Hello, my name is Getty George,
I'm Gary Wang.
and for our final project, we are working on League of Legends esports forecasting. So, probably the first question you have is, what is League of Legends? So, League of Legends is a popular video game that is really world renowned for its international competition. In it, two teams of five players take on a couple different roles and pick from over 170 unique characters, and their ultimate goal is to capture the enemy base. Along the way, they capture other objectives and destroy outposts and grow the strength of their character. The way they primarily grow their character's strength is with gold, which allows them to buy more powerful weapons and gear, and thus it is easier to destroy your opponents. You earn gold both by defeating your opponents outright, as well as taking neutral, computer-controlled monsters and characters that populate the map. Um, there are many factors such as a player's skill, certain characters that players may specialize on, the relative strength of the characters, and even more attributes than this can all influence the outcome of a match.
Yeah, so our goal is to build on the soccer match project and want to analyze a game that has a lot more information than just goals. So in this game, there are significant checkpoints that influence the end of the game. And this will necessitate a more complex model that combines different aspects that contributes to team success. And as the data would include timestamps, we want to demonstrate that we are able to refine our predictions as we feed our model more data throughout the match. So what this means is that before the match even starts, given we know the team's performance in the past, we'll be able to make a prediction about not just whether or not this team is going to win, but how much, for example, how much gold they're going to collect, and but as the team progresses, we see maybe something's going to happen. We should be able to update our model and get a different prediction and say, oh, maybe this team is more or less likely to win. Now, given that the League of Legends is very popular, there exists this freely available data set that tracks a lot of information, such as resource earned, objective taken, and all that sort of stuff. And yeah, a lot of this data includes timestamps, so which allows us to create a model that includes this time information, and again allows us to build a model that says, hey, if at 15 minutes, for example, this team is able to complete this thing, their chances of winning increases or decreases by this amount.
Yeah, so the first thing that we had to figure out was just general understanding of the data set. And so once we explored it a little bit, the next big thing was how to find what would be analogous to goals in the soccer simulation. So soccer, relatively, like rules wise, has much fewer rules than League of Legends. And a victory is directly determined by the goals you score. However, in League of Legends, there's nothing that really corresponds in such a direct way with victory. So what we started to do is investigate just correlations between different columns of data in our data set. So so if you look to the right here, this is specifically for the bottom lane roles, which go in the bottom lane of the map. And you can see how they have a positive correlation between kills and wins, negative between deaths and wins, and a and this is the big one, which is the correlation between gold and wins. And whenever you compare this to other roles, you will see that there are differences. So, for example, in this role, the if a character gets more kills, it seems that they're much more likely to win than if this player gets more kills, just because of the stronger correlation. And they both still have a very strong correlation between gold and wins. And so that primarily motivated us to use gold as one of the defining features of the model. For methods, all of our work was done in Python. And for Bayesian analysis and sampling, we use a PyMC library. This is very similar to the Julia library that we were using earlier for the soccer project. Just we decided that we wanted to implement everything in Python. This could easily be done in Julia. The first step is data processing. So whenever we download the data as a CSV, there there is a lot of organizational quirkiness, I would say, that we need to account for. And so one of those is that each match actually corresponds to 12 different rows, which is five for one team. So that's 10 total that are individual players. And then those two extra ones correspond to aggregate statistics for the entire team. And so this means that we have to go through the table to get go through the table in a linear way to try and understand what team is playing who, as that determined just by what rows are right next to each other. And so that involves a little bit of manipulation in NumPy and Pandas in order to get it to a place where our model can parse it.
Yeah, so let's talk about the models and how we're going to model the game. So just like the soccer example, we're going to use a multi-level model, which means that we're going to have some hyperparameters that's going to try to capture some common characteristics among all the teams. But also each team is going to have their own parameters that capture specific performances of the teams. And again, we're going to use previous data from off-season, previous seasons, previous results that model the strength of each team. Now we're really going to focus on three aspects of each team. Number one is their ability to obtain gold at different points in the game, specifically at 15 minutes and 25 minutes. Number two is their ability to leverage their gold at 15 minutes and 25 minutes. And third is just a general catch-all term, their skill level, which is going to include all the other aspects of including killing the enemies, the completing other objectives, stuff like that. So in specifics, each team gets a latent variable called strength. So it is a linear combination of a parameter of skill, a parameter of gold 15 weight, how much gold they have at 15 minutes, and similarly, gold at 25-minute weight, and how much gold they have at 25 minutes. The strength for team A at team B, we take the difference, call that strength difference, and that is correlated to the probability of team A winning. All right, so the sigmoid constrains the strength difference to be between 0 and 1. Essentially, if team A has higher strength, they're more likely to win. This probability of winning gets passed through a Bernoulli, and now our outcome is 0 or 1. Right, and that is the format of our data. So this model allows us to capture a few things. Number one is the ability for team to form different strategies. For example, if a team, say, chooses to prioritize gold at early game, then perhaps their gold at 15 value is going to be higher because they're able to accumulate more gold at 15 compared to gold at 25. Alternatively, they might just be better at capitalizing early game gold. So their gold weight at 15, i.e., the correlation between gold at 15 at strength is higher. We're also able to correlate between a bunch of other latent variables that we're not modeling and the strength through the skill. So for there are other parameters such as completing other objectives, stuff like that. They're all going to be wrapped up in the skill. And the effect of that is, if, say, a team underperforms, for example, in a game, when it comes to completing gold, if they have very high skill, the effects of underperforming at gold is going to be relatively small. This model also allows us to marginalize these parameters. What I mean by is this. So gold at 15 represents how much gold a team is likely to obtain at 15 and 25 minutes. So they can be trained using data, right? Data as in previous data, previous matches from previous seasons. So before the game even starts, we have an a priori of some sort of distribution. But as the game is going, we can say, hey, at 15 minutes, we make an observation and say, this team at this very particular match has some very specific gold cap. They're able to accumulate this exact amount of gold. So this distribution during the game is able to go from a distribution and collapse into a single value. The variance collapse into zero, and that means we can update our strength to a different value. So that's what we mean by updating our model during the game. We are able to go from an a priori distribution of gold based on previous matches to an actual observation of how much gold they have. And then with that, with a new strength, we're able to calculate a new probability of team A winning, and with that, a new outcome of the match. Now, exactly how the model is trained can be explained by this diagram. Here we have the observed data down here. So first of all, our outcome is Bernoulli because our data is 0 and 1. That makes sense. Our gold data are considered normal. We're saying it is model as normal because there's a lot of ways for team to get gold, and it turns out teams accumulate a lot of gold during the games. So we think it's reasonable for it to be modeled as normal. So this box down here are the observed parameters. So to fit these data, each team gets a average and a variance for their likely gold at 15. So these are the parameters that's going to get fitted. We also consider these normal, especially for the mu, right? Because teams tend to get right around about the same amount of gold at 15 minutes. It's around 25,000. We did not think it was terribly necessary to fit a hyperparameter to that because I have pretty good knowledge of the prior. That's why, for simplicity's sake, we just use a single level for that. For the gold weight, though, we don't really have a good idea of what the distribution will look like. We do know that it should really be positive because it is a correlation between how much gold they have at 15 minutes and their strength. This correlation should really be positive. It does not make sense for a team to be weaker given that they have some amount of gold. So that's why we fit it as half normal. Now, we do expect that across all the teams, the effect of having gold should be somewhat similar. That's why we utilize a hyperparameter, and the hyperparameter will be fitted as such. Skill values is a normal and is it's not a hyperparameter. We based it around 0, which is essentially a skill value is a relative skill between different teams. Now, the gold, all these parameters to the left are gold at 25, which is exactly the same as gold at 15, copied over, and the explanation is identical. Lastly, there's a quick note about normalization of data. So this gold data is sort of in the magnitude of 10,000, which ends up being quite problematic when we're trying to fit stuff to it. Not only do you need a huge variance, the way you try to combine it against skill, which is like centered around 0, or when you try to pass it around a sigmoid, which really works well for small values, it just really doesn't like it. You get pretty bad convergence issues. So that's why for our data, we essentially let's normalize it to around 1. That's why with some slides, you'll see that our gold values are in the range of 2 to 3, whereas in some slides, you'll see that it's around 20,000 to 30,000. That's just a small detail and something we learned about convergence in this project. When it comes to fitting and sampling, we use a very simple method to the mini project. You see a no U-turn sampling. And yeah, the model we're fitting the process. So the outcome, go to 15 and go to 25, they are predicted using sampling. And yeah, the bunch of parameters from the previous page were fitted. So some quick analysis before we go any further. Uh, yeah, so the posterior this predicted distribution seems for gold seems to fit within a pretty reasonable range, which gives us confidence that at least our gold is well behaving. And later on, we'll see that our outcome is also fairly reasonable.
Yeah. So what I'm showing here in these graphs is actually the distributions for all of the different teams. So we have 28 different teams. Each of them is shown in a different color. Up here you see that catch-all skill value, which doesn't correspond precisely to any one factor. But then here we have the variances for the two gold timestamps, and then the averages for the two gold timestamps. Um, One thing that I want to show is we've talked about early versus late game. And so that this kind of idea that a team could be better at generating gold in the earlier stages of the game or the later stages of the game. And so you can see that here with this light blue team here, which at 15 minutes has a below average uh, kind of gold generation level. However, you can see that once we get to 25 minutes, it is at least with the rest of the pack, if not better. And so this is just an example of a team that is better at procuring gold later, which may be a strategy that they try and nurture throughout their training. And we can see how the multi-level model has led to distributions that are similar and yet very distinct across all of the teams. Uh, so then what we tested next was our blind prediction. So this is just without feeding any like information about 15 minutes in how much gold there is or anything like that. For the untrained model with just our priors, we get a prediction accuracy of 50%, which is roughly what we expect. After training, we got an accuracy of around 62%. Um, the important point here is that whenever we first developed the model, which just had the skill parameter and no didn't take the gold at all into account, we achieved a similar training accuracy, which means that the that overall skill parameter was doing a good job of understanding how the gold played into it just inherently. So even though whenever we extracted that and made the relationship with the gold much more explicit, the our accuracy didn't increase, but it allows us to get more insight into the system. So it doesn't mean just because our blind prediction didn't increase in performance, that doesn't mean that it that the model was not worth making more complex. Um, that being said, that also means that we don't necessarily need to make the model as complex as possible. There are many factors that we are going to choose to ignore, at least in this initial exploration. Um, and we're going to focus more on the way that the gold impacts the course of the game.
I think it will be a lot easier to understand why we choose to model the gold in this hypothetical match example between Hanwha Life Esport and Team BDS. So we picked these two particular teams because Hanwha is well known to be quite good and BDS is known to be somewhat average. So this gives us some domain knowledge and that could help us check whether or not our model is reasonable. So let's just consider some gold at 15 minutes. So the gold mean for Hanwha is like around 25,400, and then gold mean for BDS is a little bit lower. So, and then let's look at the variance. Again, Hanwha is a little bit lower than BDS. So yeah, so at 15 minutes, Hanwha is expected to obtain more gold, and they're a little bit more consistent. So which is somewhat expected for a team that is considered more skilled. Yeah, we could combine these two together into an overall distribution for gold at 15 minutes, right? Because if your mean is a distribution and your variance is also distribution, you can use sampling to combine them into one overall distribution. You can also do that for 25 minutes. So it's probably easier to read as a table. So one interesting result we see is that at 15 minutes, Hanwha beats BDS when it comes to gold accumulation. But at 25 minutes, BDS actually beats Hanwha in gold accumulation, right? So this is again an example of how BDS might strategically choose to focus on late game a little bit more than early game. Let's talk a little bit about the skills next. So Hanwha has a little bit slightly higher skill score than BDS, right? So this means that all the other factors combined, or things like that, Hanwha has a little bit more ability to overcome a deficit in gold compared to BDS. Again, expected for a team that is known to be a little bit more skilled. Let's look at gold weight, or the ability for a team to capitalize on their gold. We see that Hanwha is just across the board higher than BDS. So this tells us that Hanwha is able to capitalize their gold much better. Right? So despite the fact that BDS is able to obtain slightly more gold at late game, they're not necessarily able to capitalize on that. So yeah, this shows that Hanwha is a little bit more skilled at the game. So overall, we could combine all of that and generate a estimate for who's more likely to win. So if we do not do any marginalization and we just produce a singular estimate on the probability of Hanwha winning, we get 69%. And so the overall match distribution, you get this, right? So since it's a Bernoulli distribution, so we just get 1 or 0. You count all of them up, you see that 69% of them Hanwha wins. Right? So if we take a step back and see if this is reasonable, it turns out that if you look at some other sources, in 2024, Hanwha won about 68% of all the games they played. Right? So since BDS, we chose to be in a very average team, this result is completely expected. So our model is quite reasonable.
Yeah. So now we are going to investigate integrating in this time step data. And so this is once we already have a model of how we expect each team to do, we then add in the specific gold level of a match at a certain time step. So let's say we're looking at a match here between the blue team and the red team. So we would have our prediction. Our model would already have a distribution predicted at the beginning. But then let's say that 15 minutes into the match, we take what the current gold difference is and add that to our model. And now the model should be able to predict, to forecast what team will win with higher accuracy, just because it now has more data. And as we progress from 15 to 20 to 25 minutes, hopefully the model is able to get a better and better prediction of who the ultimate winner will be. Uh, yeah, the so this is the heat map of our model. Once that initial gold at 15 minutes has been fed in, so you can see here the shaded area, which corresponds with this is Hanwha, which we've been talking about, and so we are expecting around a 0.7 percent win rate, and so we can see that as you're how this is correlated with a very slight advantage here at gold at 15. And so we're very much expecting Hanwha to do uh, better in terms of gold at 15, as we expected, as well as their win rate overall. And so then this model like confirms that, as we have now put in the data that shows that we're doing better at 15, and our uh, our winning prediction has updated accordingly. Now, if we continue to feed in more data, in this case, the gold at 25 minutes, we can see firstly that the area of the shaded region has decreased. And so this shows there's a smaller variance just in general, which makes sense as we've provided more data. And so the model is more confident in its answer. Um, you can also see it has much more of a positive slope here. And so that is showing that there's a much more positive correlation between winning and having the advantage at 25, having the gold advantage at 25 minutes.
Yeah, another way to look at it is through marginalization, right? So if we specify how much at 25 minutes, how much gold Hanwha has accumulated, what is the probability of them winning in the end? All right, so for example, we say at 25 minutes, Hanwha is doing quite average, then yeah, we'll see that their probability of winning has increased, right? It's because if Hanwha is doing average, and then we're assuming that the BDS is also doing average, then yeah, Hanwha is more likely to win because there's less time for BDS to come back. We need BDS to be doing above average for this probability to change. Now, if we say at 25 minutes, Hanwha is doing gathering much less gold than they usually do, then we see, yeah, their probability of winning is going way down. They're still slightly favored to win because some other mechanics, but we see that, yeah, they're less likely to win. If we say that Hanwha is performing above their usual performance, then we see that, yeah, their probability to win is essentially guaranteed at 25 minutes. Yeah, there are a lot of future works that can be done. So first is that we suspect there should be some coupling between the variables. So for example, when one team overperforms in gold accumulation, it is quite likely that there should be some coupling and the other team should be underperforming in gold accumulation. Right now, we're sort of assuming that they are uncoupled. So that is something that we could model in the future. Of course, there are other things we could, a lot more other factors we could model. Dragon kills, Baron kills, Champion's Drain, stuff like that. You don't need to know what they are, just know that there are a lot more things that we could add into the model, and hopefully they could increase our accuracy. Of course, we could find a data set that provides even more time step data. Right now, we only have two time steps, 15 and 20, 25 minutes. For a game that only lasts 30, 40 minutes long, that is not a lot of resolution. More time step could be a lot more interesting. And lastly, we could compare our model against existing models, right? So there are machine learning models that takes into a lot of parameters, and there's a pretty prolific online betting market that has a huge incentive to produce very high quality models, which would be interesting to compare against.
Yeah, that is our project. So thank you very much for watching.